tonight's presentation and subsequent workshop will consist of information and the implementations of various Java 8 features. A deeper dive into the collections interface than UAlbany ever had me do. A lot of examples with streams, and if we have time toward the end, some out-of-stream context examples of lambdas. But I'm confident that if you understand the streams part of the workshop, when it comes time to doing lambda expressions outside of streams, it should be pretty straightforward. Just a tiny bit of background. My name is Tyler Burke. I graduated from UAlbany last spring. I currently work as a full-stack developer for the New York State Unified Court System, and most all of our work is in Java. I mean, there's plenty of SQL and a few JavaScript, like web-based things, but all of my work, SQL and Java. And I've tried to tailor this presentation toward relaying the most useful information that I didn't have graduating from school, so that maybe some other people, when it comes time to interview or like their first day on the job, they know a little bit more about Java 8 than I did. That being said, let us begin. So, some objectives of this presentation. We're going to provide a bit of historical context for major changes that came about in Java 5 and Java 8. We're going to introduce the concept of Java generics, which many of you are definitely familiar with in at least one capacity or another. We'll then introduce functional interfaces and describe many of the most useful ones that Java 8 already has incorporated into the JDK. And we're going to provide some really atomic examples of Java streams and how the streams make use of these functional interfaces. Then we've got plenty of when I say plenty, there are 4 interactive exercises that I will explain toward the end of the presentation. And as I said earlier, if time permits it, we will have a discussion about lambdas independent of the stream context toward the end of the presentation. So just I'd feel wrong not introducing Java a little bit. Java is an object-oriented programming language. It's used widely throughout the world. While it is verbose, it is a very powerful language, and you'll see it all over in enterprise software. Java is currently owned and maintained by Oracle. Previously they were owned by Sun. But because of this, Oracle seems to support a lot of database-related things with Java, and that is why, again, Java has this ecosystem that it can succeed within. And Java runs on the Java virtual machine. There are other programming languages that have come out since Java, like Groovy and Kotlin, that also run on the Java virtual machine. And because of this, you can integrate the languages with one another pretty easily. This is a slide here that extracts a bunch of information from the Java collections interface page. I would recommend maybe going back and reading this. I'm going to post the PowerPoint after, but this is just some information about what a Java collection is. And simply, a Java collection is a group of similarly typed elements that are held in a data structure, and there are a lot of useful functions and functions and just things you can do with the collection. They extend Iterable. That's a huge one. If you're familiar with Java's for each loop implementation, it requires that whatever you are for eaching extends the Iterable, implements the Iterable interface. So we're going to move past that. You are familiar with collections, I'm sure, if you've taken Java classes before. We've got our abstract ones, list, set, and map, and then the concrete implementations of those. And I have omitted quite a few of them, but array list, hash map, and hash set. These are very easy to work with when compared to arrays. They have all of the resizing functions like add, remove, all of that built right into them. So given that we're at a point where something like an array list versus an array is not a huge memory difference, or not a significant or substantial memory difference because of the ease of use, it's generally better not to use arrays unless you're doing some really low-level code or systems programming stuff. That being said, if you know the size of things and it won't change, and you're aiming for the memory efficiency and you don't need all the collections functions, you can use arrays. There's nothing wrong with them. They work, and even these collection interfaces do use arrays in the background. So they're not all bad. Before Java 5, we had Java collections that no matter what you tried to do, they were of type object. And just about everything other than these primitive values in Java is of type object. In more modern Java, even blocks of code are considered object. The issue with everything being of type object is if you have an array list, per se, of a bunch of, I don't know, let's say strings. And for each item in the string you wanted to print out the last character, you would need to cast the object to a string. And this might seem insignificant, but it also results in a lack of type safety at compile. And the big thing about compile time is you don't need to spend any additional time trying to encounter the error. So if the compiler can tell you that there's a problem before you build the software, before you have someone go run it and play through it, you'll know that there's a problem. And without this generic type safety that I'm about to introduce, Java code was much more prone to errors at runtime. So before Java 5, this is what a collection kind of interface or collection implementation would look like. We're going to take our raw type array list. I should introduce that idea too. A raw type is an array list without a generic parameter, or without a generic parameterized type. So in this context, all of its object. The raw types are up. And we'll see here that when we try to get a value from the array and use a string member function, we're unable because we don't have that function in object. So what we would have to do pre-Java 5 is cast everything we got off the array to string, and then, only then, would we be able to use it. Now, since most of us are well past the age of pre-Java 5, we're familiar with generics already, and you're probably thinking, an array list without a type? It's become so standard to supply that type to your array list that you're probably already familiar with this idea. But, as I said earlier, these will help ensure type safety at compile. And anything that prevents you from having to run through the code to test it and see if there's problems will literally result in your employer making more money, and that's very appealing. The following slides will show you some examples of the generic, and you're familiar with some of them. So here we go. We're going to take a string list. This is kind of parallel to that last example that we did. We're going to make a list of strings. And then see when we call get there on the bottom line, we're able to use that string member. No problem. The compiler knows everything in this list has a type of string. So the compiler can confidently call to char array on every function or every element within the list. So now we're going to consider the following task. Array lists are boring and cannot triple themselves by calling a single function. Write a Java class with a superlist that implements a function to add 2 copies of every element in the list. Call this function doSuperList. And I'm going to walk briefly through what a generically typed list would look like, because we want to triple whatever the list is. We don't only want to triple integer lists. We don't only want to triple string lists. We just want to add 2 additional copies of everything that is in the list. It doesn't matter what type. So here we are. This is a generic class. We're going to call it superlist, and it will accept a type parameter that we're going to call throughout the code generic type. You can fill in generic type with whatever you want. In fact, you'll usually see a T or an E or an R or a V, just a single letter, because it's easier to write, and then you don't get as lost in characters and keeping track of everything. If you've got 2 generic types, it's easy enough to keep track of V and R. So the requirement of the superlist is that it triples itself. So what we're going to do is initialize an array list of whatever type the user wants to declare, or not the user, the programmer, us, wants to declare. And then we're going to set up a new array list. We're going to add all from the original list. We're going to add all actually, I kind of screwed it. Nonetheless, but we're going to add all of these from the temporary list, and then we're going to return. But no, that's actually fun. This actually works just the way that. And we triple the list. We see here on the output here, we start with 1, 2, 3. We're left with 1, 2, 3, 1, 2, 3, 1, 2, 3. And we're able to do this for both strings and integers because we did not use raw typing. And now we don't need to write two different functions, one that accepts an array list of strings, the other that accepts an array list of integers. This can become very tedious as you run into functions that need to accept 20 different types of lists or 1,000 different types of lists, however many different types of lists you need. Keep in mind that because the primitive data types, your ints, chars, longs, and all of that, are not objects, they're one of the few exceptions to that, we must declare their big wrapper class implementation in our array list angled brackets. You're probably familiar with this already. Array list int just doesn't work. Array list integer does. I will post a link at the end of this to more information about those wrapper classes in case anyone is unfamiliar. So now we'll talk briefly about Java generic wildcard. And Java allows for this in that you don't need to necessarily know the complete type information about this object to add it to a collection. I'm going to speak mostly of bounded wildcards today because the unbounded wildcards, while they promote flexibility, still have a ton of issues with typecasting and a lack of type safety. That being said, we've got two primary forms of bounded wildcards. And if you properly implement these, you will save a lot of development time by increasing your code's flexibility. I'll begin to talk about those shortly. So the upper bounded wildcard is notated with the question mark extends. So the format for this will be question mark, extends, and then a class. So this will accept any type that extends that specific class. Oracle has provided a great example of this, and I'm just going to walk through that. And while this doesn't seem too useful, I've put together a kind of ridiculous generic example where we put two question marks in something and we now open the door to a lot of different types. So here's the Oracle example. This is what Oracle has written on their website. We've got a shape, it can draw, a circle, it extends shape. It can also draw. We require a canvas, rectangle, another concrete implementation of shape, and then the canvas. The canvas currently has a function to draw a shape S. And we now want to make the canvas draw all shapes in a list of shapes. So we can go over here, and this is the two different ways to do this. You've got the generic version up top, where we have a list of anything that extends shape, and we iterate through and just draw the shape. And then we have the non-generic version, where we have a list of shape. And we'll see why this is problematic on the next slide. So the draw all generic is fine. We have no problems whatsoever. But because draw all non-generic is expecting a list of shapes, a list of circles is detected by the compiler as a type safety issue. So this is one example where we get the exact same functionality, but one is type safe and the other isn't. And as such, when we try to do the one that isn't type safe, we're just not able to do it. We're not able to call the function we want to call because it doesn't accept the right type. Then we'll talk briefly about the lower bounded wildcard. This is useful in understanding some of the stuff that I'll introduce with streams shortly. And this functions in a very similar manner, but instead of the class needing to extend it, the class in question must be the super type of the class that is noted in the all caps class. So Oracle, again, provides a great example of this. They have this list of numbers, and we want to add the numbers, but we want to make our function add anything that extends integer, or anything that is the superclass of integer. This is not a particularly great example, but because number is the superclass of integer, we're able to use a list of numbers for them. Now that we've introduced collections and generics, we should talk about functional interfaces. This is the beginning of the Java 8 features. Before this, we were talking. Now we're at Java 8, and those are interfaces that contain a single abstract method. If you dig deep enough into these documents, you'll find that there are other methods, but in how they're declared, they do not count as the one functional abstract method. And Oracle recommends you add the functional interface compiler annotation to describe what you're doing with it. And importantly, and what we're going to focus on today, are the existing Java functional interfaces. So this slide is a condensed list of some of the ones that we'll talk about today or are particularly used. And all of these, well, I can't say all of them. I don't think we use too much of consumer. But these will be used throughout the rest of the presentation, and we'll get a hands-on feel for them as well. So if this seems a little verbose or just hard to follow, you'll see firsthand. We're going to start with function. This is a function to be applied to an object. It returns the evaluation of the function being applied. So we're going to take an object O, and we're going, I should have put parentheses there to call toString properly. But we're going to return O to string. It doesn't matter what type O is, the result is going to be a string, and that's really important. We're going to see that later with the streams map function. Then we've got the by function. It is pretty much the same thing as the function, but it accepts 2 arguments and returns 1 result. So in this case here, in this example I've provided, we've got O1, object 1, object 2. We're going to get object 1's dollar value and multiply it by object 2's dollar value. And now we've got either an int, double, big decimal, whatever these 2 arguments are. So the next, this one's pretty straightforward to understand. It's a predicate. You can easily think of it as a Boolean expression, and the result of the predicate will be a true or false. So O, we're going to map O to, well, no, we're not going to map O, the wrong wording. So we're going to check that the length of the toString version of the object, or the object's toString return, is less than 50. This is simply an example, but we could do O dot contains whatever string we want. O dot is empty, false. O dot whatever Boolean condition we want there, we can put in there as a predicate. Then we have a supplier. It returns a value without any input. So if we want to make a supplier of longs, we'll call it random value, and we're going to, this notation here is the Lambda Notation. We've been seeing that above higher, but this one doesn't accept any arguments. I can go a lot further in depth with this when we get to the code examples, as it will be easier to explain and show. That being said, this function in particular will round the random number. That's what it will do. And the return value you get from calling that will be a rounded random number. A consumer, kind of the opposite of a supplier, takes 1 argument and doesn't really return anything. It just does something. So in this case, we're going to call a consumer of strings display exclamatory string. And the string that we are going to consume, we're going to call it S, and then we're going to print S and an exclamation point, making it an exclamatory string. Then we've got the comparator, and the comparator requires a bit more explanation than a 1-line example to kind of showcase the different things it can do. So we've got that on the next slide here. These are some comparator functions. The big one is compare. That is the function that kind of drives the comparator. And some other notable mentions here are pre-existing comparators that you can call, such as comparing int, comparing long, comparing double. We've also got reversed. We've got reverse ordering, or reverse order, and then some more complicated ones where you can map in, pass in other functions as well, where you can take an object that isn't an int, make it an int, and then compare it. But that is a little bit further along in the implementation than I feel we have good time to discuss tonight. So now it's time to talk about Java 8 stream. And then after we introduce the streams, we're going to combine what we just heard about functional interfaces and combine what we we will then know about streams and kind of work through some examples of how and why this might be used. So a stream is just a data structure, numerous elements of a given type. They were introduced in Java 8 and really enhance programming flexibility and can save a lot of time programming. If I can use a stream and I don't have a memory problem associated with it, I'd love to use the stream. It's less writing. So when I say we're going to stream something, I mean we're going to call something that implements collection and then call .stream on that function. And all of the different functions I'm about to introduce will require you to call .stream first. You're actually going to see like a chain of functions, and it all starts with .stream. So we've got many useful functions that allow you to perform computational tasks and also to manipulate data. These functions are most frequently accessed by the collections interface as stream method, but there's probably some abstract way you can access them otherwise, but we're focusing on collections, stream, narrowing it down, and they're particularly useful because they provide support for both sequential and parallel operation. So if you have some parallel processing to do, so long as you're careful, a stream allows you to do it pretty well. And this can be very valuable in situations where it is critical to run parallel. A lot of times, if you're trying parallel processing on a low resource requirement task, you're probably going to overcomplicate things with the runtime and the different thread creations. So when you're going parallel, stream or not, you should be very careful that you need to, and even better than need to, that you should, that there's even an argument to do so. We're not going to go too far into, actually, beyond mentioning it, we're not going too far into parallel programming tonight. So, that being said, the first function I will introduce is stream.count. So, it's really simple. It will tell you how many elements are in the stream. But because we've introduced the idea that all streams begin as a collection, and all collections typically have their dot size, there's no real use for this on its own. However, it can become very useful when combined with other functions. So the next one is all match. And now is where those functional interfaces come into play. So we've got our all match function, so you'd call .stream all match, and within your parentheses for the argument you're going to pass, you're going to put a predicate. And I will show a code example really quick of what all match looks like here. Cool. So we're going to go to... I actually have the example prepared for any match, but they're very similar here. So we're going to comment those out. We'll go down to the any match example. First, I should introduce this example code. We've got an abstract class that is vehicle. Vehicles have some constructors. They have a get capacity of the vehicle, set capacity, get vehicle name, all your getters and setters. We've got a toString and a get price. Great. We've got two concrete implementations of those. We've got a truck, which has a truck bed size and a vehicle identification number that all vehicles might not necessarily have, and a car that's got a number of doors and a vehicle identification number that not all the other vehicles have. Thinking about it, there should be a number of doors on the truck, and there's probably trunk space that we could add to the car, but any number of different abstractions for what a car actually is. The point is that we've got this driver class here that shows how we can use streams to better work with these vehicles, or to more effectively work with these vehicles. I will say confidently that streams are not objectively better than classical iteration methods. There are a lot of times where you'll probably drastically increase your overhead by calling a bad stream. Or you could even do things simpler by not going the stream route in the first place. However, we'll go on any match. So the any match example, we're going to add these different vehicles to the list, and I'll show you what those look like. We've got the Megacar 2021X, pretty expensive. The Megacar 2015X, considerably less expensive, but it's held its value pretty well. The Minicar 2021X, this is just cheap, it's the Minicar. The Minicar 2015X really holding its value, but it is the cheapest car we've got. We've got the UWU Truck Supreme, very expensive premium vehicle array. We've got the UWU Truck Supreme Junior, similarly expensive, not quite as bad, also released in 2021. And then we've got the UWU Truck Supreme Mini. Most of this information is kind of just to make it look like a car with these big useless model numbers and VIN. We'll focus in on the data that matters for these examples. So we're going to add all of those cars, total of 7 cars to the list, and we're going to check if the car if every item in the list, or if any item, sorry, we're calling any match, not all match. If any items in the list match this predicate. And this predicate is saying we're going to take an object that is in our stream. This can be named anything. We'll call it car, even. Let's call it car. You can change this to literally anything. It's just an identifier, not literally anything, There are rules for Java identifiers, but just about anything you'd like. We can even change it to car dollar. We want to rip. Boom. So we're going to check that the car that we're dealing with, it's going to iterate through this stream of objects. And if the car's price compared to the price we've passed to the function is less than 1, which when you're calling big decimal .compare to, it returns a value that is 1 if if the first number is greater, 0 if it's equal, and -1 if the number is less. So we're interested in anything where the car's price is less than the one we've passed to it. And here we are, we're going to run the code, and we pass it $10. And I believe everyone can see by looking at these prices here, we're going to get a return of false. Did it not run the functions? Oh, there we go. Okay, so we don't have any match for a price $10 or less than 10. That is, or no, it's $10 or less. So we can change this function just to demonstrate. Let's say we want to make it a much larger number. Too large. Number too large. Okay. So now here we have true because we have plenty of cars that don't cost this much money. That being said, we can go back to our PowerPoint here. And we see again the predicate, it's just a Boolean expression, ultimately. You're going to take the object that's in the stream, you're going to do something with it, test something. You can use conditions outside of the stream too if you have a local variable or a global variable that's useful. You could compare whatever property of whatever object to whatever you need to. And we'll see this more in further examples because a lot of these different stream methods use predicates. So next we'll talk about any match. I just demonstrated any match while I was talking about all match. The only difference, all match requires every element in the list to produce a valid result in the predicate, whereas any match requires just one or more. The test or the example would be just about the same thing, and because one of the exercises talks about any match, I won't go too much further into it. This is one of the most useful ones that I've ever found in terms of time saving and just concise, easy to read, just boom, do it code. It's filter. Filter also requires a predicate. It's an intermediate stream operation, meaning you're allowed to call other stream operations on it afterward. So we can chain this together with other things. And we'll see in the code examples that can be very useful to do complex tasks. We can remove unwanted elements from a collection, and that instead of checking 15 different properties every time in a loop, we can just only keep the ones that have the properties we want or don't have the properties we hate. And you can use numerous Boolean expressions. It's not such that you can only do one property of it. Let's say we've got that vehicle class and we want to check vehicles that are newer than the year 2020, have a cost less than $100,000, and don't contain an M anywhere in their model number. We can do that with our usual Boolean operators that say or. or and, the two vertical bars and two ampersands, respectively. The next one, actually, we'll go through an example of filter. So I've prepared an example on the same car class of filter. We'll uncomment that. We add the same 7 cars to the list, and what we're going to do is we're going to filter out all cars that we're going to accept. Well, we'll filter, I'll word it this way. When I say filter out, I mean those items won't be in the resultant list of them. So we're going to filter out any car that doesn't have the word mini or is not from 2021. So at the end of this, we will see mini cars and 2021 production or 2021 production year in our list. So we run, and here we are. Let's see what we've got in our list. We've got the mega car 2021X, production year 2021. It fits. The mini car, also perfect, meets both conditions. The mini car, it's not from 2021, but it does meet the mini requirement in the string, so we can accept that one as well. So here we go, the UAlbany Truck Supreme, model number, production year 2021, meets the requirement, 2021, and, or not 2019, but meets the requirement of mini. So instead of iterating through the list and then performing a big 15-line operation or sequence of operations, we are able to just filter the list based on the criteria we want. And there's a concept in here that I have not yet introduced, and it's the .collect function in streams. So we see after we apply our .filter, we're going to collect the items that remain in the stream, and we're going to call a collector. A collector is another functional interface, and the great part about this is that Java provides a lot of really useful collectors that already exist. So if you tune into the screen here, we can call collectors to list, collectors to map, collectors averaging double. I actually haven't used most of these things. I usually use to list, to set, or to map, and this presentation will focus on to list and to map, but you can bet that to set works very similarly. So after we've filtered it, we're going to collect all of the items as a list, and then we're going to convert those to string, or a string, the list to a string, which is what we're printing out. We're also able to use a better implementation of this. If we get rid of this toString, and it's more useful in the code for showing more than the atomic example here, we can make this an array list of vehicle. And now because this collectors.toList will return a type object, we are going to need to cast it to the type that we want. And in this case, that is array list of vehicle. So we can do this, and now we'll get the same result when we print it out, but now we can still work with S if we want to. If we want to apply another filter, we'll just go s.stream.filter. We're going to go O, our object. I like to use O, it's an object. O is really easy to type, it's really easy to remember, convenient, right index finger, maybe right middle finger if you type properly. Key to press, and we're going to filter out further anything that's vehicle name dot contains, we'll do doesn't contain mini. And in actuality, we'd probably want to just remove the other condition from this, but to show that we can put something out and then stream it again, we can, no, I've worded that poorly. We can stream something, filter it out, and then just call that on the new list. We'll do that. So we're going to reset the value of S, and now we should be left mostly with things. I've got an error. Parenthesis. We got a cast. We should be left with a list of only cars that have mini in them. We've got the, I have blundered. Oh, that don't contain mini. I'm sorry, we should have no minis in our list because of this explanation point. The mega car, these are all cars from 2021, effectively, if we combine these two list conditions. and that is one usage of filter. So now we'll talk about distinct. And distinct is very similar to filter in that it may reduce the size of your stream. So what distinct is going to do is it's going to take every object and compare them to every object using object.equals. And for any that have a match, one instance of that object is going to be removed from the list for every time there's a match. So by the end of it, you're going to have one of each item. And we've got a really straightforward example of that. So we've got this distinct example. I'm going to go down. We can even control-click, go faster. And we're going to add the same 7 cars, but we're going to add them ad nauseum. And we'll even, just for the sake of things, double that, and double that, and double that. We've got a huge list of the same 7 vehicles. But what we're going to do is we're going to stream. We're going to select only the distinct vehicles from the stream, and then we're going to collect a list and cast that list to array list of vehicle. We're then going to print out the size of this, and we should see a 7. Boom, size is 7. That's all we had to do, and we have removed all of the duplicates from the list. This can be used in combination with the other function. So you can find all of the distinct items and then sort them, or we'll get to sorting. But that is distinct. It's one of the simpler ones. There's no functional interface required to make it usable to use it. And important to remember is that objects use the object.compare2 or object.equals when using distinct. So if you've got, let's say you've got all these cars and you're comparing distinct cars, it's not going to be looking at the name of the car. It's not going to be looking at the price of the car. It's going to be looking at the entire car, the entire reference of, not just one property. However, if you want to filter based on one property, remember, we do have filter. So returning to our PowerPoint here, filter, distinct. And now we will talk briefly about find. Find first, we'll find the first accessible element in the stream. So you can combine this really easily with sorting it. Let's say you want the highest value. You'll sort in descending order, and then you'll find the first one, and you found the superlative item in the list. You could do this sorting in descending order and find the lowest or least sorted item in the list as well. But it's careful to note that sometimes this does not, without careful implementation, guarantee that you find the first item that you expect. Because if another thread is accessing the stream, you will find the first available object in the stream, and not necessarily the one you're looking for. Fortunately, many things that you'll be doing with these do not involve parallel computing, so find first will probably work as you expect it to. We've got an example of find first here. Most of these examples here, before we get into the interactive challenges and whatnot, will be they're also all using this vehicle. We're going to add the same 7 vehicles to our list, and we're going to find the first one. Let's see if we get a vehicle. Awesome. We found it. And now, what we can do, let's say we just want to get rid of that vehicle after we print it, we can remove that vehicle and then S out vehicle list, and we should have nothing left. Okay. Oh, no, you know what I did? No. So what I've done here is remove that from the original vehicle list. So we'll print out vehicle list.size. I didn't create the temporary list to hold this, or the filtered version down here, but we'll see that this should have a size of 6. Yes, we started size 7 before we've removed. And we'll see the gradient in size after we remove the object that we found in our stream. We've got the 6, and now we have the 7. Find first, if you only need one item, it's a great thing to use if it doesn't really matter which item or you know how the list or stream has been sorted. It's important to note here, and you might have seen it as I was going over that the return value for find first is something called an optional. And the gist of the optional is that you might not get what you're expecting and Java doesn't want your application to break. And this can help make these null references that might be returned by whatever you're streaming a bit easier to manage. And I will highlight what I've just described there here. So I've called or else null. This means that if we don't have a vehicle, if our optional has not found a vehicle, we're just going to assign the value of null. But something more powerful, we could do something like new vehicle. We're going to do new car. Vehicles in that class. We're going to do a new car, and then this is going to have car thing. We'll make it model number C1 production year 1995. The price we'll do new, big decimal, 20,000. Capacity 5. Number of doors 4. The VIN. Number of doors 4. So now, if we don't find something in the stream, whatever we're going to find is going to be replaced with car. So what we can do here, we'll comment this out. We'll run the function again. And notice we get the car thing, because when we tried to find first, we found nothing. So we called or else, and as such, we hit that or else, we didn't find what we were expecting. So now we've created a new car in its place. This can be particularly useful when you have a solid default class or a default implementation or something you'd like there to prevent your application from crashing. Find first, and it's optional or else. There are other functions we can call on optional. Let's remove this. So we can call find first dot oop. We're going to delete everything off the end of here, one side. Oh, you know what it is? It's because I did the concrete class. So now we're going to get rid of the or else. I'm sorry for being so slow here. We're going to get rid of the or else, and we're going to check what else we can do. We can filter it. That seems a little trivial as we're grabbing just one item, but there's probably a good use for that I'm not thinking of. Or else get, we can pass a supplier to this, which will get another value from something. We talked briefly about the supplier. We'll rewind just briefly to that. The supplier returns a value without any input, so that's similar to what we've done with the or else. But or else get is a little more nuanced in that it must be a supplier. So we're back at optional. Other options we've got here, this is one of the better ones, or else throw. New, let's call it index out of bounds exception. What is index out of bounds? Don't actually know what it will. Oh, it wants a string. Clear. Angry. Why doesn't it? Wants this. I've actually forgotten the implementation of or else throw to do this with the supplier, but we can probably do, no, it doesn't like. So we won't focus on or else throw right now, but I assure you it does allow you to throw an exception. We've got dot equals to compare that optional object in case you've got a second one. I don't know if the toString on the optional is exceptionally useful, but the optional can contain a value. We can check it unsafely by just calling .get. This, if you got the value, you'll get it. If not, you're going to get it. But .get will get the value out of an optional. So I will show what the problem is here. Notice we have required type vehicle. We're assigning the vehicle v, this value on the right here. And the provided type that we get from find first is an optional. So we need to do something with it. We have the or else, where we put a different vehicle there, or else throw, or else get, or just get. Get, little less safe, but if you know that you will have a value there, .get is fine. And that is probably far too much about find first. But it introduced the optional class. Here's some different functions on the optional class. I just talked about this, so we won't go too far into those. And now we get to stream.map. And if we see here, .map requires a function to be supplied. So we're going to take one value or one object and apply a function to that object, getting a new object, potentially of a different type. And this is where this can get really useful. Consider you have a list of dogs, and dog is an object that has 5,000 different biological attributes of the dog in addition to the dog's name. But you just want all of the dog's names. You can map a list of dogs to a list of names. Or if you wanted two traits out of the dog, you can map a list of dogs to a hash map of the dog's names and the dog's addresses, or the dog's addresses and the dog's food preferences. Basically with map, we're going to take one object, we're going to apply a function for it, and get a different object. And we will see that in our example here. Fine. Example, comment that out. We've got the map example, control click, map example. So we're going to start out with a new array list of model numbers. This is what we're going to be extracting. This is actually part of this. Array list of vehicles. The same vehicle list of 7 vehicles is being passed in. And what we're going to do is to this model number list, we're going to add all of the vehicles. We're going to stream them and then map the vehicle to its model number. We're then going to collect these model number strings as a list and ultimately add them all to model numbers. So we should expect here not to see a list of vehicles print out, but instead a list of model numbers. Awesome. We got a list of model numbers. We can rework this to do a list of any string that we've got. So for example, we could do the vehicle name. Now we've got a list of vehicles with all their attributes, and we're going to break it down to a list of their names. Awesome. We've now got all the names of those vehicles in the stream. So, continuing on, we're going to use the sorted function. And this is the sorted function with no parameters, no comparator. It's just going to use the default comparator associated with the object or the data in question. So if you're comparing two strings, it's going to compare them for alphabetical order. If you're comparing two numerical values, you're going to compare least to greatest. By default, you sort in ascending order. This is often sufficient for many of the tasks that you're doing, to just call .sorted. However, there exists a more flexible and powerful example of sorted that allows you to pass a comparator, which is one of those functional interfaces we introduced earlier. And sorted allows for you to pass whatever you'd like to the, or sorted with the comparator allows you to compare things however you'd like. And this also allows you to sort things based on numerous factors. So if you want the first tier of sorting to be based on the first character of the car's name, and the second tier of sorting to be based on the price, or for equal prices to be resolved by the, by another attribute of the car, like production year. You can do it that way. And we've got an example of that. So we'll call the sorted example. We'll walk through the sorted example. The same 7 list of vehicles, we should be familiar by now. And we're going to sort in ascending order. So we're going to do vehicle.list.stream.sorted. We're going to call one of those comparator functions, and because the data we're going to sort on is their production year, which is an integer, we're going to compare an int on the vehicle.getProductionYear. This double colon operator is essentially giving the name of a function to this comparator. So it's going to run this function, vehicle.getProductionYear, on every object in this stream, which is of type vehicle. And then what we're going to do in this case, we're just going to collect it to a list and then to string so we can print it. Then we're going to do the same thing, but for the reverse, the descending order of the string, where the highest value will be on the top. And when I say the top, the first element. And in this case, we're going to call the same exact comparator, except we're going to call another comparator function, .reverse, which will reverse the order of the string. So I will run this and we'll see how it works. We've got here the list in ascending order: 2015, 2015, 2019, 2021, 2021, 2021, 2021, and then there should be a point where it's the same. Here's the new ones: 2021, 2021, 2021, 2021, 2019, 2015, 2015. I should have separated these with a, I don't know, new order function being called. But you're able to sort things based on whatever property or properties that you would like to. And we've got an example of this in the interactive portion. So if this seemed a little abstract, it might make a little more sense when you try to play around with it. So we're going to move on. Comment this out up here. And collect. We've talked a lot about collectors with these functions, and that we're collecting these things to lists. And in the next example I show, it kind of combines a number of these different string functions, and we will also see the collectors.toMap. So, and we'll go to the combined example. Now this one will require a little more attention, but I don't think too much. So at the bottom here, we've got a list of cars. We're going to add some duplicates this time. It's the same list, but added mostly twice. I think there's like a couple elements that aren't fully reciprocated. Or no, maybe they are. But we got a big list, and what the goal here is going to do, we're going to remove duplicates with distinct. We're going to filter off cars that are older than 2021. And then we are going to collect these in a hash map and map the car name to the car price. And we're going to do all of this with one series of stream calls. So the list of names and prices, as should be map of names and prices. Let's go to refactor, rename, map of name prices. Cool. So we're going to make a map of names and prices. And we're going to cast a hash map of string to big decimal, and we're then going to call vehicle list.stream.distinct. So we're going to remove all the duplicates from the list. We're then going to filter out any items who do not meet the following condition: the production year is greater than 2020, or the price is less than this value. Or, yeah. So we're going to then collect them and collect it to a map. Now with collectors.toMap, we need to supply arguments, one for the key set and the other for the value set, or the entry set, as they call it. And we're going to take our same object, O. This is going to be of type vehicle, because we supply a list of type vehicle to vehicles list type vehicle. So for our key set, we want the vehicle name per the assignment requirement. And then for our entry set, for each vehicle, we want that vehicle's price. So effectively, way over here, arg1 equals key set, arg2 equals entry set. Okay. So what we're going to do here is we're going to find cars made after the year 2020 with prices less than, what is that? $2.3 million. So we're going to run, and we find that we've got the mini car 2021X for less than $30,000, or less than this amount of money, and then the mega car 2021X for this amount of money. And we've got a nice hash map. We can see that we iterate through the key set, print out that value within the key set, and then the corresponding member of the entry set. And here we are with our hash map. We've taken a list of some big vehicle data that have all these useless fields, and we've very quickly and on one line mapped them into a hash. And we can see here we've chained together distinct, filter. We've then collected to a map. And there is a combined example of these things. So now we'll go just briefly over a LeetCode example that I found doing LeetCode not too long ago. Given an array of integers, return true if the number appears twice in the array, return false if every element is distinct. Oh, okay. Should be easy enough. Now, how many lines you need to solve it? Not more than one. If you want to use .toArrays, and I'll show that in a second, or arrays.toList. But the way I went about this, we make a new array list, we add all the items in that array to the array list, and we're going to stream the distinct values, and then we're going to count them. And if the count is different than the number length, we're going to say that this array does not contain duplicates. Because for something to have duplicates, it would require that the filtered version has less than the original version. That's just kind of the nature of having duplicates. And that is how you might be able to use these streams to make funny looking LeetCode solutions if that's your thing. So now it is time for some programming examples. And I guess the best way to do this is I will start off, let me just check the time here. We will try to wrap up in the next, I don't know, well, this should be the end of it, these code examples. There's 4 examples, and we will allocate about 6 to 7 minutes for each example for anyone who wants to follow along. So here we go. If anyone has downloaded this and has it open in their IDE, if you go to challenges, there's a challenges package, and within it are 4 other packages. We're going to start out at challenge 1. We are going to return a list of squares with even area values. And while I have not prepared the most academic challenge type setup here, I do think that it's pretty easy to follow, and I will walk everyone through it in case it is confusing. So a square, as we define it, has a length and a width, and to print that out, we're just going to call it string or square, its length and its width. Private class, really simple. We could put this in another file, but then it just gets more confusing for such a simple example. We're then going to make an array list of squares, and that is a new array list, and we're going to add to it just these random squares. And these squares are going to produce some squares with even areas and some squares with odd areas, and the goal is to use a stream to filter it out. So the actual challenge here will consist of uncommenting this line that says filtered list, and then we're going to replace this condition with whatever predicate we want to test again. So in order to find a predicate to tell what the area is, we're going to need to think about some math and what it means to have an even area. What's going to happen is you'll replace the condition here O dot something Boolean operation something. So for example, this is the wrong way to do it. So we're going to filter anything, or we're only going to accept anything where O dot width equals 5. The answer to this is not O dot width equals 5, I assure you, but we're going to put some type of Boolean expression in here acting on O to determine whether or not that this list is, or to keep this list to only contain objects with even areas, squares with even areas. So the goal at the end is for this statement down here to print out true. And if this statement prints true, you've done it correctly. Ran the wrong file. So run this file. It's false because I've done it incorrectly, as I said. This is not the correct predicate, but we will need to pass a predicate to this function. And it's going to look like identifier, arrow, identifier dot something, and or maybe not, just Boolean logic to determine what values we do accept. And with that, I will leave the floor open to questions for the next 5 minutes or so, if anyone happens to have a question. In the absence of questions, we will just take some time to do this example.
Wait, so can you just clarify again what we're trying to do with this statement, like with this challenge? Hello?
Oh, sorry, I had silenced my microphone. Yes, the challenge is to replace the word condition with a predicate that will result in the resultant list, filtered list, only containing, I actually didn't specify what we're trying to do here. It's only going to contain squares with an even area value. So a square that has 3 length and 3 width has an area of 9. 9 is not an even number, so that square will not be in our resultant list. The only change that we have to make here is in condition, and we have to pass a predicate that's going to look something like O dot something. Less than, not equal something, or and. You just have to put a Boolean expression that will evaluate true for the objects you want to keep. That's the best way I can word it. A Boolean expression, starting with that lambda notation, the O or identifier arrow sign, and then whatever expression you want to apply to the element in this.
Okay.
And if this example is kind of weird, if this one doesn't ring well, they kind of build on each other, and they are able, I think, with an explanation, you'll be able to get the next filtrations fine.
All right, I got you.
Yep. So we'll leave the floor open for maybe another minute, and we'll go over this example before progressing into the next example. Okay, so we'll start out by defining an even number. An even number is a number that has a modulus, or has a modulo 2 value of 0. And mod 2 equals 0. So what we're going to do, the predicate that I came up with when I made this, was we're going to do O dot length, or O dot length times O dot width mod 2 equals 0. And just for the sake of being neat, we can put parentheses around this stuff. And we should see here that if I've done this correctly, our stream, or our print statement down here, will print out true. And I'll explain my test condition in just a moment. True. Okay, so we see here that our squares are even number times even number, good. Even number times odd number, also good. Even number, or odd number times even number. That's good. Those all produce even result. And this true is coming from this statement. I'm using another stream just to kind of reinforce it. And this is that no square has two odd numbered dimensions. The only way to get an odd area is to have two odd numbered dimensions. Any even number times any even number is even. Any even number times any odd number is even. It is only in the case of two odd numbers where one can possibly get an odd product from multiplication. So with this predicate, the length times the width modulo 2 is 0. We are able to filter out all values, or all squares with an odd area value, leaving only squares with an even area value. That concludes the first challenge. Challenge 2. Actually, did anyone have a different predicate? Is there anything to share about the chat? Is there any, I shouldn't just breeze past it without answering questions about what might not have been clear. So, is there anything that I can explain about the first challenge before we move into the last? All right, we're moving on to challenge 2. This challenge, we're going to create a list of names from a list of students. We've defined another private class, it's student. Students will have a first name, a last name, a middle name, an age, a GPA, an address, and whether or not they're currently enrolled. There are many situations where we don't need all of that information, and we're going to map it to a string instead to provide a more concise, or no, this is going to be a list, my apologies. We're going to map it to a list of strings instead of a list of students. So in our constructor, basic setters, I actually just use the IntelliJ generate constructor to do this. Nothing fancy here. And now we populate some students. We've got Jack Michael Frost, Melanie Carrie Frost, Mary Lou Sue, Marcus Franklin Upstart, Uwu McGee, the great Marky Zuck. And the goal here is to find and map we're going to stream student list and map all of the currently enrolled students to an array list of string. The strings in that array list should have the following format: last name, comma, first name, comma, GPA. Similar to the last time, we're going to uncomment the line below. This time we're going to replace condition with a predicate to filter the unwanted values. And then we're going to replace mapping function with a mapping function to map the values to a string. Similar to the last example, we'll go for about 5 minutes on this one, and then we'll go over the solution that I came up with for this one. Similarly, if after you're done you want to uncomment these print line statements, you are able to print out the results of tests that I've written. So once again, the goal is to find a list of all of the currently enrolled students and map them, instead of an array list of students, to an array list of string. And this can all be done here with this post-stream list assignments. I also realized that throughout here, I haven't really stopped, other than on that last example, to ask if people had any questions or needed clarification on some of the things that I've introduced, wanted an expansion into some of the things I didn't go too far into, anything like that. At any point, either now, after, even a week from now, you have any questions about this, about Java, anything whatsoever, you can direct them directly to me via Discord private message. You can at me in a public channel. Whatever you want to do to get in touch with me, and I will do my very best, or just short of it, to answer the question that you... We've got another 2 minutes on this one. If anyone is just getting started, the goal once again is to replace to map all of the currently enrolled students to an array list of strings that contains the student's last name, the first name, and the GPA for each currently enrolled student. And we accomplish this by replacing condition with a predicate, which is that Boolean expression that must evaluate to true, and then, we're going to replace mapping function with a mapping function that will kind of direct the data into the form that we want it, or map it, per se. So here is the function that I had come up with, or the series of stream calls. We're going to take our list of students, we're going to stream that list of students, and then we're going to filter it. And our filter condition, we're going to filter is currently enrolled. So only students where this is currently enrolled flag is set to true will be contained in the stream after this function finishes. Then what we're going to do is map the remaining filtered elements of the stream, or the non-filtered elements, depending on how you want to approach that linguistic designation. We're going to map the last name plus, and what happens here is we have a string plus another string, so the compiler already knows we're going to string. I mean, with the first string, it kind of establishes that. But once you add a plus to a string, you go to string concatenation. So we've already mapped it to type string, and then we're going to take the last name, a comma, the first name, a comma, and then the GPA. And we're going to collect that in a list per the assignment requirements. And now we're going to print out whether or not none of them match the following ones that should have been filtered, and also the size, or whether or not the size is 3. I'll tell you the size should be 3, and these 3 individuals should not be in it. So we're going to run it, and perfect. These 3 individuals are missing. We've used none match, and that means the string can't contain Zuck, Jack, or Marcus. And the size of the list is 3 because we filtered out 3 people from a list of 6. Great. Now, on to challenge 3. And if you followed challenge 2, you'll notice a lot of similarities between challenge 3 and challenge 4. We just do slightly different stream operations and use them in sequence. So challenge 3, we're going to use the stream. Actually, this one's a really simple example. This is the easiest example we do, I think. So if you haven't done any of them and you want to, this is a great one. So we're going to use the stream to see if any students are failing. And the goal here is to determine whether or not any active students, i.e. students that are currently enrolled, has a GPA of less than 1.5. We simply need a true or false value here. We don't need who those students are. We just need to use a stream.anyMatch with a valid predicate to see if any students are both active and failing. And then after that, we're going to print out the value of that Boolean we've evaluated, and hopefully it should show true. So again, the two conditions we're testing for here in our predicate are active students and GPA less than 1.5. This one is going to be a little bit shorter in terms of time because it is simpler, and I want to allocate adequate time to the last example and then a wrap-up period where the relevance and importance of this and how it applies to my everyday life can be discussed, and how it may apply to the lives of those who are leaving school and going into enterprise Java development. So that being said, another minute or two to work on this one before we introduce the final chapter. All right, so here we go. Our predicate, or at least the predicate once again that I've come up with. We're going to take an object, and then we're going to do O.is_currently enrolled because we want active students, and O.GPA less than 1 point. So if we have a student that is currently enrolled and has a GPA of less than 1.5, that is any match. So it only needs to be one. It doesn't need to be the whole list. We're going to hopefully get a print of true. So have any students failed? We see here in the data that they have, and yes. Oh, I ran the wrong function. But yes, they have. True. Yes. So we have a failed student. We actually have 2 active failed students. No, just 1 active failed student, and that would be Uwu McGee with a GPA of 1.0. Yes. So now we're on challenge 4. And this, we're going to create a list of student names sorted by their GPA. And this puts together some various different stream functions. We've got 3 blanks to fill in this time. And I'll go over the task again. We've got a very similar, if not almost identical name of list of students. Maybe I changed the GPAs around to make the sorting more enticing or more demonstrative of something. But it's pretty much the same thing. And the challenge here is to stream the student list and map all of the currently enrolled students to an array list of strings that should have strings that read like this. First name, comma, last name, space, 2 hyphens, and then the student's GPA. And this list must be sorted by GPA in ascending order. Given 3.9 is the highest GPA in our list for an active student, that will be the last item in your list. This is just included, so in case you're doing it and you want to know if you did it right, that will be the last element. Similar to the last time, we're going to uncomment the line below, this post-stream list equals, and what we're going to do is replace the condition with the conditions we're filtering on, and we're going to replace the comparator for sorted with the comparator we're using, and then we're going to replace the mapping function with whatever mapping function we want to use to map the student to a string. And we'll do about 6 minutes for this example and then bring everything to a close. So if you want to give this one a shot, this combines 3 different stream functions, actually 4 if you can count the provided collectors to list. You can run the print lines at the bottom to see if you've done it correct, and I will go over the results. So about 4 more minutes on those. About 2 minutes remain until we're going to go over this one. If anyone has any questions before we go over the answer, I'd be happy to answer them now. All right, so I'm going to begin going over the answer now, or once again, the answer that I came up with. There might be numerous solutions that you could come to with this. But here we go. We're going to start by replacing our filter predicate with, we just want to find the active students. So we're going to do the same thing. O dot is currently enrolled. We filtered out all non-active students by only accepting the ones that are currently enrolled. Now we need to use a comparator. And for the sake of simplicity, I used one of the default comparators, or one of the existing Java 8 comparators that I introduced earlier. We'll call comparator dot comparing double. And then what we are going to compare is O dot GPA. So we're going to compare every object, in this case every student's GPA, to one another to sort them in ascending order. Now we must map these to a string, or, well, ultimately to strings to be added and collected to be put into a list. So what I thought of for the mapping, it's almost identical to the other mapping. O dot first name plus comma space plus O dot last name plus comma space or no, it's not comma space. I wanted a space, 2 hyphens, a space, plus GPA. O dot GPA. And while I did not make any of these member variables private because we're using the private classes, when you use getters, your accessor methods more appropriately, you'll be able to do this just the same, like O dot get first name, O dot get last name, O dot get GPA. All of that will work just fine, but because we're working with a private class in the same function that it's declared in, we're okay to just use the member variables. But this is not restricted to private classes. You can use these in any classes. So now we're going to see what the results are. First, we'll print out the list so we can see everything. We're going to make sure it doesn't contain the people that it shouldn't. And then we're going to check that the first element is the student with the lowest non-failing GPA, or just the lowest GPA in this list, which is 2. So we're going to print, run, and we've got McGee, Melanie Frost, and Mary Sue with GPAs of 2.0, 3.2, and 3.9 respectively. So once again, what we've done there, we're filtering the predicate or Boolean expression we're going for. The filter is the object is currently enrolled, or the Boolean value that is called is currently enrolled evaluates to true when it's checked by the filter. We're going to sort by the comparator that compares doubles to one another on the student's GPA. So every student in the stream will have its GPA compared, and that's how they will be sorted. And then we're going to map. We're going to take an object of type student. We're going to map it to the student's first name plus a comma. And at this point, we've already established that it's a string variable or a string object that we're dealing with because Java casts concatenated strings to strings, or strings concatenated with most anything to strings. That's fine. Then the student's last name, some hyphens, and the student's GPA. And we can see down here that we got exactly what we expected. We can even do plus \n to put them on their own line. I could have probably done that a little better with respect to this. Nonetheless, this is the final example or challenge 4 that combines these different stream operations. And now, before I open up the floor for final questions, I would like to talk about some of the relevance of this and my experience getting into it. So when I graduated school, I was on the hunt for jobs. I had actually started applying before I finished, and I eventually interviewed for a few places, didn't really get anything. I interviewed for the court system. I got the court system job, and I was thrilled to hear that they were using Java for like all of the application. I was kind of bewildered by it even, but thrilled because I did a lot of Java in school. I started Java when I was 13, although didn't pursue it very ambitiously. And it was great to know Java. And I learned that I didn't really know too much of enterprise Java. I had a decent understanding of how to interact with basic data structures and use algorithms, but a lot of the ways I would go about solving things were not modern or up with the times. And when I first started looking at the code that we use at work, I noticed there were a lot of notations that I didn't even understand. Like some of the more complicated generic examples, I'll even rewind to the beginning. When I saw something like here, something like this, we had an array list and then a question mark, it extends map, and you can actually do like question mark, extends something, super something. You can chain these generics together as far as you need to address whatever data that you need. I didn't understand that. I had no idea like what that was even saying. And as I came to accept that I would need to learn it, I started doing some reading into it, and it actually makes a good deal more sense. And as I started to understand these generics, I was able to read the Java docs for things like the functional interfaces, like your suppliers and your consumers. And as such, we deal with a lot of object relational mapping objects. So we've got SQL databases, thousands of different tables, and there's all sorts of different data contained in those. And we have Java classes to represent them. So let's say there's a family court file. It's got different file members. You know, you've got a complainant, you've got a petitioner, you've got an interested party, you've got a treatment service, mental health expert, whatever that may be on this file, like that's a unit of court documents, a file. A lot of times we don't need all of those associated objects. We don't need to pass around thousands and thousands and thousands and thousands of bytes of data if all we're interested in is perhaps the name and the party's role. So we're able to map to a hash map of name and role for each of those file members. A very recent example, I have to generate an alert when someone has an order of protection that requires them to submit their weapons. I've used a stream implementation to do this. We get all of the orders of protection on the document, and if any of them contain, or all the terms on an order of protection, if any of them happen to match that short description value of 12, which is surrender your weapons, we collect that to a list and we add it. Instead of manipulating down through that whole thing with a big for each loop for every term on this, we're going to cast that to a string and do all of that. You're able to produce lines of code or blocks of code that can be much easier to follow than a big complicated list iteration or any sort of collection iteration. It is also useful even to begin to understand these things just because the documentation is a little more complex than a lot of the things you may have been exposed to in school. And if you can follow the Java docs on these things that have question mark is a superclass of T and question mark extends R, if you can understand that stuff, you'll notice that there's a lot more different just Java docs, and for other libraries, not just the default JDK and not just JDK 8. There's like Java 8 is old now. It happens to still be very relevant because the enterprise world can't keep up with Java's updates, but there's even more features. Java, you can now declare a generic or just like a var, and Java will figure out what type of data you have, which is present in a lot of other languages. But being able to understand what some of these things mean and how functional interfaces and generics work will allow you to do a lot of different things in Java when manipulating collections. And a fundamental understanding of the collections interface is really useful when it comes to dealing with large-scale software because it's a part of it. You will have collections. That being said, I'm no Java master nor Java expert. I'm sure if I were to show this to someone who really knew what they were talking about, they'd scoff at me and like, why did you do any of this stuff? There's probably some other implementation that might be a little better or a little stronger. You know, maybe they could explain optionals in a better way than I could. But I've really tried to tailor this toward the information that I've acquired since leaving school and passing that on to people so that they can at least begin to start thinking about how to apply this stuff, or maybe they could apply the stuff, or at the very least be able to read it when a class or a document, a tutorial, a Stack Overflow post talks. That being said, I shall open the floor once more for questions, comments, concerns, feedback, whatever it may be. I will stop talking for a minute or two, and yeah, there we are. If anyone has any questions, comments, concerns, something else, let me know.
Tyler, I was wondering what stack you use at your job.
Java. It's a little more complicated than that. So we use Java for our program front end and back end. It's Java Swing. We have tons of libraries of in-house Java, like Java Swing expansions and extensions. But at the core of it, it's all Java 8, Java Swing. We use Oracle's PL/SQL for our database. And as such, we have a custom, because this software is about 23 years old. And when it started out, there was not things like Hibernate. So somebody at my job made their own OR mapping library. And we still use that to this day. Nowadays, if you were starting over, you would not write your own OR mapping library because people got paid millions and millions of dollars to make things like Hibernate and make them work perfectly and make them apply to every aspect of industry application that you can think of. But that didn't always exist. So we are actually in a huge situation of technical debt because everything uses even Java Swing. Like the modern answer to Java Swing, Java FX. Java Swing has been consumed into Java FX. But the nature of our budget and our development team size results in us just sticking to the Swing. That being said, we do program everything at the interface level, so if anyone ever wanted to make web-based GUIs, we could do that. Also in our stack, for some of our web-based products or services, we do use JavaScript. I think the framework we use for that is React. Yeah, the stack is pretty simple, honestly. It's Java. We make usage of a lot of XML parsing for our OR mapping. And that is a big mess of a headache. I might one day try to do some kind of presentation on OR mapping once I've made my own OR mapping library to go over. That's a project I'm working on. Other stack details. No, I don't think there's really too much. No, I think it's pretty much just Java, PL/SQL, little JavaScript, a lot of XML. We use XML schema files that are XSD, but they're pretty much just more restricted XML files. We use a network monitoring alert system called Zabbix. It's free and open source and might be cool to learn about. What else? The Topaz signature pad for collecting electronic signatures. We use an alternative version of something called Xdoclet, called Ydoclet. It helps with a lot of the OR mapping stuff. We validate our code using PMD. It's an external library that checks for all sorts of programming warnings and errors and imposes constrictions that force good code that a normal Java compiler wouldn't. PMD is pretty cool, albeit very frustrating when a seemingly okay null check breaks the whole integration build. That happened a couple weeks ago to me. Further, we use Gradle as our build tool for most everything. Before Gradle, we had used Ant, and there are still remnants of the old Ant code in there, but Gradle allows us to build our massive software using parallel processing. And I cannot stress enough that with large-scale applications, build times, even if you're using good optimized technology, they take a while. And let's say you shave off, let's say you build 4 or 5 times a day. You're building stuff 4 or 5 times a day locally, and you can shave 5 minutes off of that build each time. You save 20 to 30 minutes just because you've used a good build tool, or you've reduced your build time by finding compile time errors instead of running the whole software, building it for 15 minutes, and then finding that, I didn't put the type for this array list, or gotta rebuild and cast it. You're able to save a lot of time by avoiding those runtimes and by using parallel processing where it is appropriate. A lot of our SQL queries will go on tables that have millions, quite literally millions of entries, and we might have, in the worst case scenario, 100 users running that at the same time, or like 1,000 users doing that. So we want to resolve it as quickly as possible, so we're able to use 16-core parallel processing. But on other queries, we don't want to do that at all because the query is small enough such that it's a waste of time spinning up all those threads. I kind of digressed from the question of what is our stack like, but it's Java.
That's I'm surprised that your team was using Swing, but I guess if the code base was, first created 23 years ago, it makes sense.
Yeah, and as a result, we have to, I just spent the last week or so trying to modernize an old Swing implementation that we had for the print queue. And to deal with some of those older technology, when I first started, I was using a JSortable table. I think JSortable table has been deprecated since Java 7. And trying to hook up a modern, it was just a mess. It was a mess. So trying to pick the best technology for what you're doing, or at the very least, adequate technology, goes a long way, and you can save a lot of hassle with things. I think that the project at the court system is a little unique because of just the state-funded nature of it, the age of the application, this can't-fail mentality. The show goes on with this department no matter what. While we do have deadlines and schedules and build things, if the build doesn't happen on the day it's supposed to, we're doing what we can. It's going to happen. So we're able to deal with these technical debt issues, but I imagine if this kind of thing were happening in a private sector job, the whole company would fall apart. They'd hire a new team of developers and write a whole new application. But because we have thousands and thousands and millions of bits of data of important court documents, we can't lose any of it. We don't have the time to rewrite all of it. There are thousands of different tasks and tens of thousands of different classes within a project. So while Swing is suboptimal, we can push forward development in Swing because everything is already developed in Swing, and we have a whole backend library to implement Swing MVC. That's another detail. I haven't mentioned it at all here, but the model view controller design pattern is very useful to know. I believe, 418Y introduces it, but I never took that. So if you haven't read about model view controller, that one will almost surely follow you into the industry. The other major just design pattern concept is to read that design patterns book. There's a group of people called the Gang of Four who wrote a really famous paradigm shifting programming book called Design Patterns. Pick it up. Another reading recommendation, anything to do with the paradigm that's called software craftsmanship. It kind of just encourages you to do things correctly, not take shortcuts, and do things in a way that you are a craftsman and not so much a worker. That being said, I don't have too much left to say on the subject of Java 8 for tonight. I will be hosting another workshop tomorrow on unit testing, test-driven development, and what we're going to do there is we're going to develop a small Java application using test-driven development. And as a quick teaser for that, this is after we do some unit testing stuff. I'll introduce JUnit, how to set up a quick JUnit project and stuff like that. But the test-driven development, the concept at play here is that you develop the unit test before you actually program the component. And the important detail is you have to develop a good unit test that you're confident when that test passes, that component is ready for production or deployment or just to program something else. So you start by making the test, you run the test fails because you haven't done the programming, you program it to the test, and because your test is good and robust and complete, once that test passes, you have the confidence to move on. And this is really useful too because you already have the tests for when you upgrade the software. I'll also talk about regression testing and all of that good stuff tomorrow night at 8 o'clock. And I'm out of stuff. If there's any more questions, comments, or concerns, I will answer them. Otherwise, I will probably depart in about 5 minutes.
If there aren't any other questions, I guess we're probably good for tonight then. But yeah, thank you, Tyler, for giving us the presentation, and obviously it's very good to see Java in this other perspective. So thank you, and I'm sure your presentation tomorrow will be just as good.
The presentation tomorrow will be a lot more applicable. While I will be using Java libraries, this follows you all over the place. Unit testing is not specific to Java. So this one, that will be a very useful one. And I will say, I was unprepared at my interview to talk about unit testing. I did not have any libraries for this that I was familiar with, any paradigms that I'd practiced, none of it. And I still got my job, but I wish I could have gone to that interview with that knowledge. And you will find it all over the place. So I would like to thank everyone sincerely for coming. I'm really glad. I had this crippling fear that I'd be here and there's only going to be 1 or 2 people. Then when I got here for 3 minutes, there were only 1 or 2 people. So to see everyone show up, it warmed my heart. And once again, if anyone needs help with anything related to computer science, general science, hell, even English, or the extent of my French, I'm more than happy to help you with it. Just contact me by whatever mechanism you can, and I will do what is in my immediate power to resolve that for you, or refer you to someone that can resolve your issue, or lead you to the solution. Thank you very much.
Thank you, Tyler. And alright, so yeah, thank you everybody else for coming. And so just to kind of close out the meeting, so as Tyler mentioned earlier, so Tyler will also be giving a presentation tomorrow on unit testing. And yeah, just to go off of what Tyler was saying, it's definitely very big on it can be very big for new grad positions, and it can be listed in new grad job posting descriptions. So it's definitely something really good to know and can set you apart from other applicants. And then in terms of other events, on Friday we're going to have a company come and talk to us. The company is called Source, and they're from Syracuse. And so they're basically going to give a little bit of a panel presentation, and then at the end we're going to open up the floor to students and let them ask different questions to the industry professionals that came to speak. And so that meeting with Source will be at 7 p.m. and it will be in ES 241, which is Earth Science 241, and so it'll be in person. And before that meeting, there's also going to be a resume critique session that the engineers from Source will be hosting, and that's going to be at 3:30 p.m. And so that's going to be in the business building, and we will be talking, I believe, we'll be sending out some more information about that, or I believe I put that in the announcement. No, I did not. Oh, yeah, no, I did not put that in the announcement this week. But so it'll be in the business building, and we'll provide a little bit more information about that. And at 5 p.m. So the resume critique session will be from 3:30 to 5 p.m. And then at 5 p.m. they'll be going over to the campus center, and they'll be having a little bit of a dinner. And so only they only want a few people, only a few different people are able to come, so it's capped at about 4 or 5 people from the IEEE. So if you are interested in going to that dinner with the engineers from Source, if you, please just let me know, and you can DM me on Discord. And if we haven't hit 4 or 5 people yet, then you should be all good to go. But yeah, so that's about it. And yeah, so thanks everybody for coming, and thank you again to Tyler. And if nobody has anything else, then we're all good for tonight. So good night, everybody.
Good night. Thank you.